Hello everyone. In this video, we are going to talk about thin-walled pressure vessels. You probably have seen and used pressure vessels a lot, and we want to talk about the thin wall. And you might say, well, the pressure vessels are probably what you see in oil and gas refineries, petroleums, and so on, right? Holding gas under pressure like these pictures that you can see. But that's not really all of the pressure vessels that you can see. Even an aircraft cabin is a pressure vessel. Space vehicles are pressure vessels. The pipes can be pressure vessels. There are lots of other things that I mentioned here, like, for instance, even a fire extinguisher could be a pressure vessel, right? And spray cans, stuff like that. All of these can be pressure vessels. So it's not really necessarily something that you see in oil and gas industry or petrochemicals. So if we want to look at the stress inside these members and make sure that we use thick enough walls so they don't basically deform or go through fracture or anything, we need to study them a little bit. And so the first thing we want to talk about is when we say thin wall, right? What does that mean? Means typically the ratio of the radii to their thickness is at least 10 to 1. So if this guy is, let's say, for instance, 4 meters in radius, then the thickness of this wall should be 0.4 meters or below. Okay, so that is a ratio of radius to thickness of 10 to 1 or more. So this is a thin-walled pressure vessel. Now, we're going to look at first spherical ones, and then we are going to look at cylindrical ones. So a spherical one, like this one, if you want to find the stress in it, you're going to, and here we assume that internally there is pressure P in it, and the radius is R, and the thickness is T. So these are the important parameters. And as I said, R over T should be bigger than or equal 10. And P here, before we move on to stress calculation, P here is gauge pressure. It's not absolute pressure. So this is measured with respect to the outside ambient pressure. Okay, so P here is the difference literally between absolute pressure inside and the absolute pressure outside. This is a gauge pressure. Okay, it's a relative pressure to the ambient. So that's why from outside we did not put any air pressure, because that one with this relative one, basically by considering this relative, it's basically like canceling this component. Okay, so keep that in mind. Now, here we are going to cut it in half by a plane and look at one of the halves. So this is like the left side. Now on this internal surface of the hemisphere here, hollow hemisphere, the pressure P is acting. So the total force acting in that horizontal direction is going to be P, the pressure, the gauge pressure, times the cross section in front of the pressure, which is this cross section, and that is pi r squared. So this capital P is the total force to the left. On the other hand, the sigma, the stress, should be multiplied by this basically donut shape here. Okay, you have to find the area of that. That is where the sigma is acting to find the total force to the right. Now, how much is the area of this donut? Well, the thickness of it is d, the radius of it is r, or in this case rm. I tell you what rm is. So 2 pi r, the circumference of it, 2 pi r times t, that's the area, which is what you can see here. So that is the area of that disk multiplied by sigma. That's the total force to the right. P times pi r squared is the force to the left. You set them equal. Now, what is Rm? Rm is the average or the mean radius of this guy, because if you look at it, there are two radii really, right? There is an internal radius and an external radius. R here is the internal radius. There is also an external radius, which is R plus T. And then the midpoint of this the midpoint has radius rm. So rm is really r plus t divided by 2, or r plus t over 2. Okay, this is what you have. So that multiplied by 2r is the circumference of this middle circle here, and times t, that's the area. Now, this is what I said. Now, for thin-walled pressure vessels, this T over 2 can be basically neglected compared to R, because remember, R over T is bigger than 10, so R is at least 20 times bigger than T over 2. And if I can neglect this factor of 20 here and say Rm can be approximated by R because T is not so big compared to R, and replace this by R, now I can get rid of a pi and 1 R here. And so solving for sigma, you're going to find sigma to be PR over 2T. If it was not a thin-walled, then you could not do it. You still have to use this relation, and in that case, sigma will be basically pi times r squared divided by 2 times r plus t over 2 times basically t. Okay, so this is the general formula. If it's not thin-walled, and if t is almost 0 compared to r, and we can neglect this, then you will get to this one. So PR over 2T, that's the stress inside a spherical pressure vessel. And it doesn't matter which direction you cut. In any direction that you cut the sphere, it's a symmetric about any axis or any plane. So you can see that if you look at any element on this sphere, on any face, there is only this sigma. Okay, and there is no shear stress, there is only normal stress. So clearly these are the principal stresses as well, because there is no shear on the face of that. So sigma here, PR over 2T, that is your sigma 1 in this case. Okay, and that is your maximum stress that can happen on this material. Now if you look at it in 3D, and look at the elements, here we can look at the elements on the outside or on the inside of the spherical pressure vessel or the tank. So if you look at it on the outside, like this picture here on the outside, so this is the sphere and this is that 3D element here. Now of course there is a sigma and a sigma, but on this outer surface that is exposed to air, there is no pressure or no stress. So in that direction, that sigma is equal to 0. Yes? So in this case, I can say that sigma x and sigma y are both equal to the sigma PR over T, but in the z direction, sigma z equals 0. So it's a stress, it's a plane stress scenario. And so if you look at the Mohr circle that I taught you in the previous video, since both of these are the same point and sigma 3 is 0, all three circles will collapse to 1, right? So if I want to go back and talk about it, so 2 of your points fall here, and the average is, since they are equal, the average is going to be on that same point, and then your 3 is going to be here, so you only going to have one circle like that. And the tau max here, if you wanted, this tau max is of course equal to half of sigma, and since sigma is PR over 2T, tau max is going to be PR over 4T. Now why do you care about tau max? Because these tanks, these spherical pressure vessels, are typically made of basically ductile material, and ductile material would fail under maximum shear stress. So the T max, this one, should be less than or equal T allowed if we go with the Tresca method, which is the maximum shear stress. If we use one Mises, then we have to use all of them. But clearly here is the state of the stress on an element outside. Now, if you look inside, if this element goes a little bit inside, so now when you look at this element, still on the X and Y, you have sigma, but this bottom surface here, this guy, this bottom surface, this one here, underneath it is this pressure P. So sigma equals negative P for the bottom surface. And so the state is going to be sigma z is negative P, but X and Y are equal to sigma. And in this case, you're going to get another number. So if, again, I draw the Mohr circle, so this could be a good practice for the Mohr circle. This is your tau, this is your sigma. You have two numbers here, and then the next number is here. So this is negative P. These are that PR over 2T. And the biggest circle that you can get here is this guy. And so the radius here, which is equal to the tau max, this radius is, of course, this sigma plus that pi divided by 2, which is what you can see over here. Okay, and since sigma is a function of P, so it's going to be P over 2 times R over 2T plus 1. This is the maximum shear stress. So if you want it anywhere on this spherical tank, what is the maximum possible shear stress anywhere in the tank? That is this guy. This one is your maximum, what is your maximum shear stress, because this is bigger than this top one here. Because you can see this is PR over 40 and then plus P over 2. So clearly this is bigger than that by P over 2. And so for that reason, this is the maximum potential shear stress anywhere in the spherical tank. Okay, so now that we have seen this, let's look at one example here with numerical values, and then after that we can go to cylindrical pressure vessels. So here we have a compressed air tank. It is keeping air under pressure, and the diameter of it is 18 feet. The thickness is 1.75 inches. You clearly see the radius is 9 over 1.75 inches. It's really a big number, way more than 10, correct? Because this is, you have to divide it by 12 to get it into feet, okay? And then this is 9 feet. So the ratio is way bigger than 10. And clearly this is a thin wall pressure vessel. Now, the way that they formed it, they had two hemispheres and then they welded it. So that is the weld bead that you can see. And this is how they made it. Now, if the allowable tensile stress in the steel, this is the maximum tensile stress in the material of this tank, is 13.5 KSI. And by the way, KSI means kilo PSI. So if this is this much, then you want to know what is the maximum possible air pressure PA in the tank. And here, this is a subscript. The same thing for this one, right? So this one should also be a subscript here. Okay, so that is part A. And then part B, it says, if the allowable shear stress, maximum shear stress in the steel is 6,200 psi as opposed to 13,500, how much is maximum pressure due to that? Call it PB. Now, if the normal strain at the outer surface of the tank to not exceed 3 over 10,000, what is the maximum permissible stress pressure PC? And here we assume that the material is following the Hooke's law, and the Young modulus is 2910 to the 6 psi, and the Poisson's ratio is 0.28. D, if you have measured the strength of the welded bead, right, and you know that this welded bead cannot carry any tensile load more than 42 kilo psi per inch of the weld. Now, if this minimum safety factor for the weld is 2.5, how much is the maximum pressure here, PD? And finally, considering all of these together, what is the final maximum allowable pressure? So you see, in order to determine the maximum allowable pressure, you have to consider several things. The maximum normal stress in the tank material should not exceed the maximum value sigma allowed. The maximum shear stress should not basically go above the maximum shear stress. So we are basically looking at both methods of failure: maximum normal stress, maximum shear stress. We also make sure that the normal strain doesn't go anything more than that. We don't want the dimension of this tank to change significantly. And finally, we look at the maximum normal stress on the weld. Okay, now you might come up with another one, maximum shear stress in the weld as well. But typically for weld, we go with the maximum normal stress here. And so with all of this, I want to know how far I can go up in terms of pressure in this tank before the failure happens. Okay, so how do we solve? Okay, so the first, for part A, we learned that the stress, the normal stress, the maximum that can happen is PR over 2T. And if this thing is at most equal to 13,500 psi, with the thickness of 1.75 inches, so we convert it to feet by dividing by 12, and this radius is 18 divided by 2, that is 9. From here, we can easily come up with the first maximum pressure, PA. So we solve for P and call it PA. And PA, if you calculate for it, is 437.5 psi. This is maximum for no failure due to maximum normal stress. Scenario B, here you want to look at maximum shear stress. We learned that the maximum shear stress was PR over 40. Now, actually, the maximum shear stress is this one, if you want to be very accurate. Okay, but here, if you look at this, I can go with this one as well. In the book by Jure and Brooks, the simpler formula is used, this one, but actually it's better to go with that because that is going to limit it. So if I want to be really accurate, instead of this, I should really use the one that we just had, P over 2, and then times T, basically R over 2T plus 1. This is the correct way to do it, calling this PB, and maximum shear stress is 6,200. Again, we have the numbers for R and T. Remember, this is R, this number is T, and from here I should be able to solve for PB. So the number is going to be 389.2 psi. Okay, now if you look at the book, it's 401.9 because this portion is not considered. But you see, if I consider that, I should go with a little bit smaller pressure. Now for part C, the normal strain on the outer surface. So on the outer surface, if you remember, on the outer surface, what scenario do we have? This is the scenario, plane stress. And what we want is the normal strain, correct, to not exceed that value. Now, how much is that? So epsilon x is equal to 1 over E of sigma x minus nu sigma y minus nu sigma z in general. And in this case, there is no z. Sigma x and sigma y are both equal to PR over 2t. And E is also given to us. This is 29 10 to the 6. And this should be at most equal to 3 over 10,000. And again, R and T are given. So if I call this basically P sub C, everything is known except for P sub C. If I solve for P sub C, your number is going to be 391.6. psi, very close to the previous one. Now part D, on the weld, okay, on the weld you want the maximum basically normal stress to be how much? So this is 42,000, but there is a safety factor of 2.5. So your sigma max, which is still pi r over 2t, and you call it PD, this should be equal to that 42,000 divided by the safety factor 2.5. Okay, so clearly you have to pay attention to that portion. And if we solve for P, now one thing you have to pay attention to is this 42,000 that we just have, kpsi. This is per inch of the weld. Okay, so the unit of that is also going to be psi. And from here, if you solve for PD, this is going to be 311 psi. So now if you look at all these different pressures, clearly you have to go with the minimum one. And so this is the ultimate P max, or P allowed, if you want to call it P allowed. This is the maximum pressure that you can have, so nothing is going to fail. And you can see here the weld strength is the dominant factor. And you cannot just go with the safety factor of 1 for weld. You have to go bigger because welds are most of the time not perfect. There are cavities in them, which significantly reduces their strength. Okay, so we typically use a bigger safety factor for the welds. Okay, now if it's a cylindrical pressure vessel, then of course it's not symmetric about all different axes. It just has one axis. And so you're going to get two different stresses. So when you cut, one cut is going to be longitudinal cut like this. The other one basically is going to be a lateral cut. So you either call it along the length or you call it along the radius. This is actually the top one is a radial cut. This one is a longitudinal cut, if you want to call it. But basically here, you're going to get two separate stresses. The first one is sigma 1, which you can see here. That is called the circumferential stress. Circumferential stress. Sigma 1, because it is on the circumference. Sigma 2, which appears parallel to the axis, is called longitudinal or axial stress. Okay, so we have circumferential stress, sigma 1, and sigma 2 is called longitudinal or axial stress. And these are different values. And if you look at any element on the tank basically here, or the pressure vessel, sigma 1 is in this direction, in the radial direction, and sigma 2 is in the longitudinal direction. So what are these? If I cut it this way, then the inside pressure is going to be multiplied by this cross section here to get the equivalent force. And this side of it is 2R, and this side of it, you consider it arbitrary B. So it is going to be 2RB times P. That is the force inward. The force outward is going to be sigma 1 times what? So each one of these small rectangles that you have, the thickness of it is T, and the width of it is B. So it is going to be sigma 1 times T times B, but you have two sets of that, so it's going to give you 2 sigma 1 TB. That should be equal to 2 PBR. And simplifying your longitudinal, your circumferential stress is going to be PR over T. On the other hand, for longitudinal one, the pressure P is going to act on the circle, which has cross section of pi r squared. So that is the force inward. The longitudinal one, sigma 2, is going to again work on this disk, which has a radius of r, or r average, and thickness of 2. So 2 pi r t times sigma 2 That's the force outward. This is force inward equal to them. And sigma 2 is going to be the same thing that you had in spherical, PR over 2T. Okay, so while your longitudinal for cylindrical tank is the same as the stress for the spherical tank, but in the circumferential, you have 2 times bigger stress. Okay, and this is the difference between these 2 types of tanks. And of course, looking at these 2, you can clearly see that a spherical tank is better because the maximum stress in it is smaller, okay? And they are the same in both directions, X and Y, but the basically cylindrical tank will get some bigger stress for the same radius and for the same thickness. Okay, now of course they have their own advantages. The advantages, you can only expand them in one direction, and the other direction you can limit it. You can make them as long as you want. Sphericals, they extend in all directions, so they are a little bit less comfortable in terms of space for basically containing anything under pressure, right? So sphericals take a lot bigger space in all directions. Spherical only in one direction, really, and or more in one direction. But again, sphericals are the best in terms of resisting high pressures. That's why you see gases under very high pressures are typically stored in spherical tanks. Okay, in cylindrical ones will keep gas, but not typically as high pressure as these guys are. Okay, so going back now, if you want to look at the stress elements on the outside and inside of the tank, so on the outside of the tank, as I said, the outside of that element is exposed to the air, which has no pressure, no stress. So in one direction you have sigma 2, the other direction you have sigma 1, and your tau max is going to be half of sigma 1, again, because if you look at the Mohr circle, you have one stress here, one stress here, and one is 0. So this is your sigma 1, this is your sigma 2, which is half of sigma 1, and this is 0. So clearly your max shear stress is going to be equal to sigma 2 or sigma 1 over 2. Now, if the element is on the inside, not only you have sigma 1 and 2, on the inside you also have sigma z equal to negative pressure. And in this case, if you look at your 3 sigmas, your Mohr circle is more interesting because you have sigma 1 and you have sigma 2, and then you have negative pressure sigma 3. So the biggest circle in this case is the one going from sigma 1 to 3. That's this guy. So if you want the tau max, that is the absolute biggest one, that is this guy here, that is really going to be equal to the radius of this, which is sigma 1 minus sigma 3 divided by 2. And that is this value here. This is the maximum potential tau that you would get anywhere inside the cylindrical tank, but outside it's just PR over 2T. So you clearly see that if you factor this out, it is going to be P over 2 times what? Basically R over T and then plus 1, right? And this is PR over 2T. If you go back and look at these ones, look, this was P over 2. Oh, sorry. This is P over 2 R over 2T. So it's going to be a little bit smaller. Plus 1, that was R over T. So you're going to get bigger shear stresses as well, of course. So this 2 here does not exist. Okay, so these are the stresses in thin-walled spherical and cylindrical pressure vessels, and we solved one problem, and we revisited the Mohr circle for the elements inside and outside these tanks. So it is a practice on the Mohr circle as well. Hopefully the video was useful to you. I'm going to see you in the next lecture. Thank you.